Okay, we're going to start with section 4.5. This one is L'Hopital's rule. So we're going to write out what does this rule mean. So we'll write it out first, and then we'll talk about a couple examples in this part of the video, and then we got a couple more parts to finish out the section. So for our theorem, this will be L'Hopital's rule. What this says is we're going to assume we have a function f of x and a function g of x, and we want to let them both be differentiable. So assume that both of these are differentiable on an open interval containing a. And we need f of a equals g of a equals 0. So both f of a and g of a equals 0. We also assume that g prime of x is not equal to 0, except possibly at a. Then we get the following thing. The limit as x approaches a of f of x over g of x will equal the limit as x approaches a of f prime of x over g prime of x. So what we're saying here is, as long as f of a and g of a equals 0, you'll get the form 0 over 0. You can, to compare the limit or evaluate the limit, you can take the derivative of the top and the derivative of the bottom and look at x equals a for that. However, this only holds if you're in the form the original limit is in one of these indeterminate forms 0 over 0. If like the original limit is 7 and you take the derivatives of the top and the bottom, stuff's going to get messed up. We say if the limit on the right exists or an infinite. So we get this holds if as long as this limit of the derivatives exists. Exists or is infinite. And by infinite we mean positive infinity or negative infinity. So as long as when you go to compare the derivatives, if you get the limit on the right exists or it's an infinite limit, this is okay, and this L'Hopital's rule holds and is true. This also holds, so this conclusion also holds if f of x and g of x are differentiable near a, and the limit as x approaches a of f of x is equal to one positive or negative infinity, and the limit as x approaches a of g of x is also equal to positive or negative infinity. And this also holds, so this also holds for one-sided limits. Okay, so that is our theorem. The next couple examples we're going to kind of unravel like what exactly is going on here, how do we use this, because with all of this, all these words down here, it gets kind of confusing as far as like what actually, how do we use this? I see that there's a limit, the original functions, and there's the derivatives. When can I use it? How do I use it? And all that stuff. So we'll do a couple examples to answer answer that. So first example is we're going to look at the limit as x approaches 2 of our function x cubed minus 8, all that over x to the 4th plus 2x minus 20. So first thing is these both appear to be continuous functions, so we're going to try plugging 2 in and see what does the limit approach. So if I put 2 into the top here, 2 cubed is 8. 8 minus 8 says the top is approaching 0. If I put 2 into the bottom here, 2 to the 4th is 16, plus 2 times 2 is 20. So 16 plus 20, or sorry, 16 plus 2 times 2 is 20. 20 minus 20 is 0. So we are in form 0 over 0. So this is what this f of a and g of a, if they're both equal 0, then the limit as x approaches a would be 0 over 0. So this form here, 0 over 0, says it's okay to use L'Hopital's rule. In previous sections, we would have tried to like factor the top and factor the bottom and cancel something they have in common. But now we have this nice tool that says, okay, well, we can apply L'Hopital's rule. So we can use L'Hopital's rule. And what we get is the limit up there. Since that limit up there was formed 0 over 0, we're able to use L'Hopital's rule. And we're going to take the derivative of the top. So the top becomes 3x squared minus 8. When you take the derivative of 8, it just goes away. The bottom, we'll take the derivative of it. So that's basically, again, L'Hopital's rule says, look at the derivative of the top, divide it by the derivative of the bottom, and look at the limit after you do that. So we get 4x cubed plus 2. Derivative of 2x is 2. Derivative of negative 20 drops. So now if we try to evaluate the limit of this, if I put 2 up here, we get 2 squared, which is 4. 3 times 4 is 12. And that's over, if I put 2 down here, 2 times 3 is, or sorry, 2 to the 3rd is 8. 8 times 4 is 32. 32 plus 2 is 34. So we get 12 over 34, and that fraction reduces down. 12 divided by 2 is 6, and 34 divided by 2 is 17, I believe. And we get 6/17 is the answer for our limit. So this is easier than trying to factor and cancel. But again, to use it, you have to be in this form here, 0 over 0. If you're not in 0 over 0 form or infinity over infinity form, you can't apply L'Hopital's rule. So we're going to look at second example here. We want to look at what is the limit as x approaches 2 of 4 minus x squared, all that over sine of pi x. Put like a little different color band in here to kind of keep our examples separate from each other. Okay, so we get, we want to evaluate this. So we say, okay, what happens if I evaluate this at 2? I get 4 minus 4, which is 0, over sine of 2 pi. Sine of 2 pi is 0. So we are in form 0 over 0 again, so we're okay to use L'Hopital's rule. If we got like 0 over 3, that's not the right form. It's not 0 over 0 or infinity over infinity, so we wouldn't be able to apply L'Hopital's rule. So let's see what we get here. Take the derivative of the top. Derivative of 4 is nothing. The derivative of negative x squared would be negative 2x. We're still looking at the limit as x approaches 2 for this one. When we take the derivative of sine, we're going to have to use the chain rule. So derivative of sine is cosine. Leave the inner part alone. And then we multiply by the derivative of the inner part. Pi x has derivative pi. So here is our new limit. If I put 2 in for x, negative 2 times positive 2 is negative 4. That's all over. Cosine of 2 pi is 1. And that would be times pi. So we get negative 4 over pi for our answer to that one. Okay. So again, you have to verify that your form is correct before you apply L'Hopital's rule. But the actual application of L'Hopital's rule is just take derivative of the top of the fraction, derivative of the bottom of the fraction. All right, so we're going to take a look at example 3 here. Oops, let's use back to our green color here. All right, so this one says we want the limit as x approaches pi over 2 of cosine squared of x, all that over 1 minus sine of x. So when we look at this, cosine of pi over 2 is 0, so the top becomes 0 squared. The bottom is 1 minus sine of pi over 2 is 1. So we get 0 over 0, so this is 0 over 0 form again, so we're okay to use L'Hopital's rule. So we use L'Hopital's rule. We're going to use that. That's going to say take the derivative of the top and the bottom. Our limit is still approaching what the original limit approached, so we're looking at limit as x goes to pi over 2. The new top, we have to use a chain rule. 2 comes down. We leave the inner part cosine of x alone. And then we have to multiply by the derivative of cosine, which is negative sine of x. In the bottom, the 1 goes away. We have negative sine of x. So we're going to take the derivative of negative sine of x. And the derivative of negative sine of x, well, the derivative of sine is cosine. The negative's out front, so it's going to be negative cosine of x. And before we do anything else, we're going to note the cosine of x here and the cosine of x here can cancel. That's going to leave me... You always, as you do L'Hopital's rule, whenever you get your derivatives, you always want to simplify them to make sure... I should say also before we do this, the negative down here should be able to become positive. It'll cancel out with the negative up there. So I'm left with basically 2 times sine of x over 1, which is 2 times sine of x. And if I look at that, as you take the limit as x goes to pi over 2, sine of pi over 2 is 1, so this is 2 times 1, so we just end up with 2 for the answer of our limit. So we applied L'Hopital's rule, and that got us to a form. We were able to cancel the cosines, and then we noted that the negatives were able to cancel out to positives, and our kind of messy division that we had originally turned into a, after we took the derivatives using L'Hopital's rule, it turned into an easy to work with function. So we're going to look at another one of these. And then we're going to kind of pause on part 1 here, and the rest of it we'll do in the second part. So for this one, we want to figure out what is the limit as x approaches 0 from the right of x natural log of x. And we should remember, we said when we wrote down all the L'Hopital's rule here initially, we say this also holds for one-sided limits, so we could use L'Hopital's rule on one-sided limits. The problem here is, initially, when we look at this, if we look at what happens as x goes to 0, well, as you go, x goes to 0 plus, just x itself goes to 0. And that's being multiplied by, as x goes to 0 from the right of natural log, that's going to head down to negative infinity. So we're in form 0 times negative infinity. This is indeterminate. But what we need to do is we need to convert to form 0 over 0, or like infinity. Could be positive or negative, like you could have negative infinity over infinity. We need to convert to one of these two forms, basically. So the easiest trick, if you have x, you can move to the bottom of a division as x to the negative 1. So we're going to use this trick here for this one and say, well, the original one, if I algebraically rewrite this thing, I could say instead of x, I'm 1 over x to the negative 1 times natural log of x. And then I can say, well, natural log of x is the same as natural log of x over 1. So this will be limit as x approaches 0 of natural log of x over x to the negative 1. Natural log of x, if we just kind of look at its graph looks something like this. And 1 over x, if we look at its graph looks like that. So when we put that together, we get the form here. As you go to 0 to the right of natural log, that's negative infinity. As you go to 0 from the right of, and this I wrote this a little badly. It's not x minus 1, it's x to the negative first power, the way we have it there. So as we go to 0 to the right of x to the negative 1, that goes off to infinity. So we're in this infinity over infinity form, which is now a form that we can apply L'Hopital's rule for. So now that we've got it down where we're in negative infinity over infinity, we'll use L'Hopital's rule. And we'll say, all right, that's going to be the limit as x approaches 0 from the right. Derivative of natural log of x is 1 over x, which we could write as x to the negative 1. And downstairs you have negative x to the negative 2 when you take the bottom derivative by the power rule. X to the negative 1 over x to the negative 2. You can algebraically cancel an x to the negative 1 in between them. So that will leave you a 1 over x to the negative 1. We said 1 over x to the negative 1 was actually the same as x. So this negative out front says this will be the limit as x goes to 0 from the right of negative x. And so if I let x go to 0 to the right, then just x goes to 0, and we get 0 for our limit back on that one. Let's just make sure that the book agrees, and it does. So we're all good with things up to that point. So. Again, use L'Hopital's rule. You need to get a indeterminate form of a certain type, and then once you verify you have that indeterminate form, take the derivative of the top and the bottom, and then if you're in an indeterminate form but it's not the right type, you can use tricks like rewriting an x as 1 over x to try to get it in the form where you have a division, and then check if you are zeros over zeros or infinities over infinities. So we'll stop there for this part.